Now, let's talk about mapping, function, and relation. So, we are going to start with relation, and hopefully, by the end of this video, you should be able to differentiate between these three different quantities. So, let's begin with relation. What exactly is a relation? Think about it. What would you say if you ask a such question? A relation is a set of input and output value, typically an order pair. Because when we say an order pair, it means you are comparing those value in coordinate form. So if you have something like this, this can be considered as a relation. Let's say you have A, comma B. So these two values, A and B, are both relation, even though they are variables, yet they are still a relation, which implies that the first value that's present in the coordinate bracket parenthesis is known as the x value, which is known as the input value, while the other one, which is B, is known as the y value, which is the output values. So that's how it works. So let's understand this more better. Let's consider a set of order pairs like this. How can we relate these two values using a relation or using the concept in a relation? There are some things you need to know about relation. There's something we call domain and range, and we also have a range of a relation. The domain of a relation is the set of all the input value that are present in a particular relation. And keep in mind, to list out the set, it has to be arranged in ascending order. Similarly, that of range is the set of all the output value that are present in that particular relation, and at the same time, it must also be listed in ascending order. By the way, you can also list it in descending order, but always work with ascend. This, as you are seeing right here, is an example of a relation. We have two different ways of representing relation. The first way is by using set notation, which is what you are seeing right here. The second way, which is often used, is known as the arrow diagram. We are going to consider that as well. So, how can we find the domain of this kind of problem? You need to keep in mind that this is an input. Let's say x1. This is also an input. The first value that is present in those parentheses, consider them to be the input value. So this x3, x4, and x5. So the set of the input value, which is the domain, is simply A, B, C, and D. Now you need to keep in mind that the repetition of a certain value is irrelevant. You need not to repeat a value if it turns out to be present more than once. Just writing it once is enough. What about the range? The range is the set of the output value, that is the y value. So this is y1, this is y2, this is y3, y4, y5. So it tends to be the same A, B, C. Um, D is not among the range because all the output has just A, B, C, A, and C. So D is not among the range. And that is a quick and easy step to identify or figure out the domain and the range of a particular relation. So how can we represent this relation using the other way of representing relation, which is known as the arrow diagram? Okay, I will need to get rid of this. By the way, hopefully you have seen that. So the first thing you want to consider doing is to draw two oval shape. For instance, just work with that. I think it's pretty much perfect enough. So the first oval is meant to insert all the input value respectively. Okay, keep in mind you have to arrange it in ascending order, and sometimes it might not be that way. But regardless, if you are the one forming it yourself, please kindly make sure you arrange it in ascending order. So I have A, B, C, D. Excuse me. So which implies that the first over is meant for the domain, while the second over is meant for what we call the co-domain. This is domain, this is co-domain. The question you would like to ask is, why is it not the range? Yes, it's all because that is how it is being attached to this concept. It turns out that whenever a relation is represented using set notation form, all the output value tends to be the range. But whenever it is represented using the arrow diagram, it might not be all the output values that will be the range. That is, not all of them might have or might be serving as an image of a particular input value. As we get forward, as we get further into this topic, you will guess what I'm saying next sense. So for this, I have A, B, C as the output. So they will now be relating those input and output value together with an arrow. So for the first order pair, X is A, the input is A, and the output is A. I have it this way. The second order pair, that is B being related to B. For the third, C is being related to C. And for the third order pair, D is related to C. And this is the arrow diagram of the particular relation. So let's consider another example so as to understand this to the higher extent. Let's assume we are to list the domain, likewise the range of this particular relation. And at the same time, we should represent it using an arrow diagram. So that will be the first thing we are going to consider. So we said for the first over, then the set of the input value is said to be embedded. So this first input, second input, and third input. That's A, C, and E. And we said for the second over, the output respectively is said to be inserted. That's Y1, Y2, and Y3. So I should have B, D, F. Now the next step we'd like to do is just to begin to be producing those inputs to the outputs respectively. So over here, A is mapped or being related to B, and C is produced to D, and E is produced to F. And this is the arrow representation of the particular relation. Now, how can we list the domain? Likewise, the range. The domain will be the set of all the input value that is being arranged in ascending order. So that will be A, C, and E. And the range will be the set of the output value, that's B, D, and F. And this is the solution to this problem. By now, you would have understood or understand the basic idea behind relation. Now, let's move forward. We have types of relation. We have different four types of relation, which is what we're going to look into right now. And here are they. The first one is known as reflexive, second is known as symmetric, while the third is known as transitive, and the last one is known as the antisymmetric. Problems involving these four types of relation is often common as students do find it confusing, most especially when it comes to this third one. Hopefully, by the end of this video or by the end of this aspect, you should be able to understand the difference between all the four. Just stay calm and stick with me. For a relation to be reflexive, every input must be produced to itself as an output. Okay, what am I saying in essence? Let me consider an arrow diagram that consists of a particular input A, B, C. Then let's say the output is of this form C, D, or let's say CBA. CBA. If the relation is such that A is produced to A, B is produced to B, and C is produced to C, then such kind of relation is said to be reflexive, as its name implies. Reflect. It must be mapped to itself, or it must be related or produced to itself. Now, since it is a relation, you need to keep in mind that a relation can be of this form, or it can be reflexive if it is like this: A, B, C, and you have B, A, C. A is mapped to A, or A is related to A, B is related to B, and C is related to C. Then we have A again to be related to B. This is still reflexive relation. Okay, it's still a reflexive relation. All right. So that is when a relation is said to be reflexive. Now, what about the next one, which is known as symmetry? When is a relation said to be symmetry? Now, I short it for you people for easy understanding. A relation to be symmetry, it has to be arrow back, meaning that if a unique input is produced to another unique output, then that output must be produced back to that input. What am I saying? Let's see what I'm saying makes sense. I have A, B, C, D. I have A, C, B, D. A is produced to A, B is produced to B, C is produced to C, or C is produced to D, then D is produced to C. This is an example of a symmetric relation. Why? Because it has an arrow back. C is serving as an input value in the first place and is being produced to D this way. Now, it turns out that that D, which is the output, now come to be produced to C again as an input. Then, in that case, they are said to be symmetric, which is called the arrow back. If at all you can figure out that D is not produced to C, then in that case, they are not symmetric. It must have an arrow back. So your main goal will be to figure out an input that is produced to another output, but that output is not being produced to that input. Once you can figure out a situation like that, then consider such relation not to be symmetric. Another example of a symmetric relation for easy understanding, let's consider this. A, B, C, then C, B, A. So A is produced to B, C is produced to A, and B is produced to C. Then I said C is produced to B. Okay, let's stop right now. Is this kind of relation, is it symmetric or not? Our main goal is to look for a unique input that is produced to another unique output, whereby that output is now not produced back to that input. Once we can figure that out, then it is not symmetric. A is produced to B. Is B produced back to A? No, B is not to A. Therefore, this thing right here is not symmetric. This is exactly what I mean. Even though C is produced to B and B is produced back to C, we already have one that alters the condition of symmetry. So therefore, it is not a symmetric relation. I believe you should get that point by now. Let's move to the next one. Before I discuss about transitive, I would like to talk about antisymmetric first because it's just the opposite of symmetric. If this one is arrow back, this one is arrow not back. If arrow is back, then it is not antisymmetric but symmetric. What are we saying? A is mapped onto C, B is mapped onto B, C is mapped being produced onto C, then A is produced to A. Is this kind of relation, is it antisymmetric or not? Your main goal is to look for a unique input that is produced to another unique output, whereby that output is now produced back to that input. In a case like that, such relation is not antisymmetric. Once you can figure that out, then it is antisymmetric. A is produced to C. My main goal is to look for C being produced to A. Since I can't figure out C being produced to A, then I can partially say that this is antisymmetric. Let me look for another one. B is produced to B. That can never alter any condition of all this. Okay, I don't think there's any other unique that is produced to another unique output. So this stuff right here is antisymmetric. Okay, this thing is antisymmetric relation. So when is it now not going to be antisymmetric relation? Let's see. Okay, don't let me get rid of that for now so that we can use it to compare. So let's say that I have A being produced to A, I have B being produced to C, then I have C being produced to B, I have A being produced to B, then I have B being produced to A. What type of relation is this? Is it antisymmetric or symmetric? Don't forget, if you want to check for symmetric, your main goal is to look for a unique input that is produced to another unique output, whereby that output is now not produced back to that input. Once you can figure that out, it is not it's not symmetric rather. If you want to check for antisymmetric, your main goal is to look for a unique input that is produced to another unique output. But that output is now produced back to that input. You can see it is just the opposite of them. For symmetric, it need not. For antisymmetric, it must. That's when they will not be symmetric or antisymmetric. So let's check that. A is produced to A. We don't need that. We can never alter it. A is produced to B. That's it. A is produced to B. We can see it right here. Now, is B being produced back to A? Once we can see that, then it is not antisymmetric. We can see that B is produced back to A. This stuff right here is not antisymmetric. So let's see another one. Is there another unique input being produced to another unique output? C is produced to B. That's it. C is produced to B. Okay. Is B being produced to C back? Yes. Damn, this thing right here is indeed not antisymmetric. But it turns out that it meets the condition for symmetric. Therefore, this stuff is not antisymmetric but symmetric. And that's just it. Hopefully by now you should have get the pattern on how these types of relation works. Now, the last one, which usually seems confusing, but I want you to just stay calm and check how I'm going to disclose it with you. For transitive relation, that one is called shortcut. It means for all x is an element of a particular relation, or let me say x comma y comma z, x comma y comma z is an element of a particular relation. Relation. For such relation to be transitive, you must be able to identify the input being produced to another output, and that output is being produced to another output again. You now look for a shortcut whereby the first input is produced to the last output. Once you can figure that out, then it is antisymmetric. Otherwise, it is not antisymmetric. So let's see. So I have a ray diagram. I have A, B, C. I have B, C, A. If A is produced to C, and I observe that C is produced to B, I need a shortcut whereby I can move from A to B without getting to C. According to this diagram, before I can get to B, I must move from A to point C. It is now point C that will now take me to point B. But I need a shortcut whereby I can get from A all the way to B without passing to point C. If this occur or take place, such a relation is transitive. So therefore, conclusion is that your main goal is to look for the condition not to take place. Once you can figure out that the condition does not take place, then it is not transitive. You get my point? Perfect. So let's consider an example. A relation R is a set 1, 2, 3, defined as R to be in set notation to be order pair. We should check whether R is reflexive, symmetric, antisymmetric, and transitive. So the first thing we'd like to do is to represent that relation that is in form of set notation in or using arrow diagram. That will make it easier for us. So I'm going to draw my first over, and the second one beside it. Oops, should I just work with this or I should draw it again? Let's just continue with that. So for the set of input, that's 1, 2, 3, then that's all. Just 1, 2, 3. 1, 2, okay, let me give space, and 3. And for the set of output, that's 1, 2, 3 as well. So that's 1, 2, and 3. So let me begin the order pair now. I should be comparing them with each other. So for the first order pair, 1 is related or produced to 1. For the second one, 2 is produced to 2. That's nice. For the third one, 3 is produced to 3. Okay. For the fourth one, 1 is produced to 2. 1 is produced to 2. For the fifth one, 2 is produced to 3. 2 is produced to 3. Then for the sixth one, 1 is produced to 3. 1 is produced to 3. Good. Now my main goal is to begin to answer those questions one after the other. Is this relation, is it reflexive or not? What would you say? Think about it. Use everything we have been discussing so far to check if it is reflexive. For a relation to be reflexive, an input must be produced to itself. And it turns out that all the input value over here tends to have themselves being reflected back in this relation. So therefore, it is reflexive. Don't bother about 1 being produced 2 again. Once it has already produced itself, it's reflexive. 2 produce itself and produce 3. It's still reflexive. Your main goal is just to check that does all of them really being reflected by themselves. Once you can check that out, then it is reflexive. Otherwise, it is not. Perfect. Next, are they symmetric? Is this relation is it symmetric or not? The condition for symmetric is that there must be arrow back. If a unique input is produced to another unique output, that output must be produced back to that input. Otherwise, it is not symmetric. It is observed that 1 is produced to 2, but unfortunately, 2 is not produced to 1. Once I can figure out one condition that alters the condition for a relation to become symmetric, then the stuff is not symmetric. Next is antisymmetric. Is it antisymmetric or not? What do you say? Pause the video and think about it. For antisymmetric, we need not the arrow back. If a unique input is produced to a unique output, then that output need not be produced to that input. If that occurs, it is not antisymmetric. If it doesn't, it is antisymmetric. 1 is produced to 2. 2 is not produced to 1. That's perfect. 2 is produced to 3. 3 is not produced to 2. That's interesting. Therefore, this stuff is antisymmetric. I believe you get the points now. The one being produced to 1, those ones are irrelevant. We don't need them to alter the condition. We are looking for separate input compared to separate output, not same input to same output. You understand? So last one is transitive. Is it transitive or not? We said transitive is a shortcut whereby you move from one point to another point, and that point you move from there to another point. Now we need a shortcut whereby we move from that first point to the last point. Once we can figure that out, then it is transitive. 1 is produced to 2. 2 is produced to 2. That doesn't work. We don't need that. 2 is produced to 3. Is 3 produced to another thing else? No. Let's check. 1 is produced to 3. Is 3 produced to another thing else? No. This stuff, well, I think we can figure that one out. 1 is being produced to 2. 2 is being produced to 3. Wow. And 1 is now being produced to 3. That's interesting. That's a great shortcut. I move from 1 all the way to 2. And I move from 2 all the way to 3. I need a shortcut where I move from 1 all the way to 3. And it tends to be present. Therefore, this relation is transitive. So it implies that this relation is all the 3 types of relation or all the 4 types of relation except symmetric. Look for many problems and solve in order to develop your ability in this aspect. Let's move on to mapping and function. So, what exactly is a mapping? How does it relate to function? And how do both of them relate to a relation? Both mapping and function are relations, but it's just that they have condition before they can be considered as that. A relation is said to be mapping if for every input value in that relation has one and only one output value. In a case like that, such relation is said to be a mapping. So, what am I saying? Let's say I have an arrow diagram this way. I have A, B, C. I have B, A, C. If A is mapped, or yes, is produced to A, and B is produced to B, and C is produced to C, then such kind of relation can be considered as a mapping. For every input value, there is one and only one output value. Now, there's another way in which you can add a relation to be a mapping, and this is what I'm saying. I have A, B, C, then I have C, B, A. If A is produced to A and C is produced to A, B is produced to B, and B, yes, I think it's okay this way. Then it is called a mapping. Yes, this is a mapping. It is not a mapping if B now goes to C. It has altered the condition for mapping. But in that case, it is a relation. You get what I'm saying? For every input, there must be one and only one output. You understand? One input must not have more than one output. You can see now, B is now having B and C. So this is not a mapping. That's what I'm saying. But if two inputs are having the same output, this can still be a mapping. You understand the point? So that is how mapping works. Now, what about function? What is the difference between mapping and function? I must disclose with you, mapping is a function. The difference is that in function, we deal with numbers, typically real numbers. While in mapping, we can deal with numbers, we can deal with letters, and we can deal with words. We can relate anything with one another. But in function, only numbers can be dealt with. So that's just the difference. Mapping is a function. Before a relation can become a mapping or a function, every input value of that relation must have one and only one output value. Now, unlike that of relation, we also have two types of mapping, which is known as one-to-one mapping and onto mapping. We also have types of function, which should be our last discussion in this video. But for now, let's focus on type of mapping: one-to-one and onto mapping. What exactly are they? But first, you need to be familiar with some basic notations that we use when it comes to mapping and function. So let me get rid of this. The first one is how to represent a mapping between two different sets or between two different things. It can be in two forms. Let's say X, capital X is a set, and lowercase y is also a set. Also a set. Then lowercase x is an element of uppercase X, and lowercase y is an element of uppercase Y. Then, if there is a rule that assigned element in set X to another element in set Y that assigned X and Y together, then such rule is considered as mapping, as we have been doing so far. So therefore, we can say that F, which is known as function or mapping, okay, is such that set X, okay, is being mapped or is being produced onto set Y. So this is a symbol for mapping or a function. Another way is that they can use the element in them. That f of element in X, that's lowercase x, is equals to element in Y, that's Y. Okay, lowercase y. If A is an element in set X and B is an element in set Y, they can also say that f of element in set X, which is A, is equals to element set Y, which is B. So those are two ways in which they can represent mapping and function. But in most cases, something like this is often used. F of X is equals to Y, meaning that the function of the input value is equals to the output value. Okay. Now back to one-to-one function mapping. So when is a relation said to be one-to-one? A relation is said to be one-to-one if different elements in the domain, you already know what the domain is, that is the set of inputs, has different elements in the codomain. You know the codomain, which is the set of the output values. Then in that case, such mapping is said to be one-to-one. So what are we saying? If I have this as an arrow diagram, my bad, don't mind my diagram. Okay, I have A, B, C, and I have B, A, C. So if A is mapped to B, and B is mapped to A, and C is mapped to C, then this is one-to-one mapping. Every element in the domain is mapped to, yes, it's mapped to different elements in the codomain. That is, a single input must not have more than one output. Different, they must be different. Different elements in the domain must be mapped to different elements in the codomain. Otherwise, it is not a one-to-one mapping. Exactly. So domain. Another example of that is this. Okay. Let me use a real number right now. I have 2, -1, and I have 0. And I have 4, 5, I have 6. So if 0 is mapped to 4, 1 is mapped to 6, and 2 is mapped to 5, then this is one-to-one mapping. Different elements in the codomain or in the domain has different elements in the codomain. Now, what about this? What would you say about this? Let me get rid of this. Is this a one-to-one mapping or not? So I have 2, 3, 4, 5, for instance, 1 being mapped to 2, 2 being mapped to 2, 3 being mapped to 5, 3 being mapped to 5. Is this a one-to-one mapping or not? What would you say? What would you say? Now, it turns out that more than one input an element in the domain is having same output as the element in the codomain. Therefore, this stuff right here, this mapping is not a one-to-one mapping. Okay, it's not a one-to-one mapping. And that brings us to the next types of mapping, which is known as the onto mapping. Okay, that brings us to the next one, which is known as the onto mapping. Now, there's one more thing I want to say about the one-to-one mapping. If not all the elements in the codomain are used, that doesn't alter the condition for a particular um, relation or mapping to not be one-to-one. A, B, C, D. If B is mapped to C, C is mapped to D, and A is mapped to B, this is still one-to-one. This A, don't let it confuse you. Since it doesn't has an input, then leave it that way. Okay, leave it that way. It is still a one-to-one mapping. You understand? So let's move on to onto mapping. When is a mapping said to be an onto? Now, for an onto mapping, all the elements in the codomain has to be used. I just said something recently that for one-to-one, it's not necessary that all the elements in the codomain is used. But for onto, all the elements in the codomain must be used. All of them, that is the range, is equal to codomain. So let's consider this diagram. Okay, and let's say I have A, B, C. Let's say X is mapped to A and Y is mapped to B. Z is mapped to C, and W is mapped to B. Now, it's this one. Is it a onto mapping or a one-to-one mapping? This stuff right here is not a one-to-one mapping because more than one input is having same output. More than one input is having same output. So this thing is not a one-to-one mapping, but an onto mapping. This one is completely an onto mapping. You can see that Y is mapped to B and W is mapped to B, and it is all the codomain that is used. So therefore, range is equals to codomain here. Range is codomain because if I'm to list the range is just A, B, C. And it turns out that the element in the codomain 2 is simply A, B, C. So this is how to identify if a particular mapping is one-to-one or not. Okay. Now let's focus on the types of functions. Okay. Let's focus on the types of function. So by now you should have been able to differentiate between mapping and the relation. Okay. Now we have three types of function, which include the injective function, the surjective function, and the bijective function. So when is a function, I said when it comes to function, we'll be using numbers. We are not to use letters or anything else. When is a function said to be injective? Now it will be very easy for you because you already knows one-to-one mapping. One-to-one mapping is the same as an injective function. Okay, it's the same. That is, for a function to be injective, for every input values, there must be one and only one output values, and different input values must have different output values, but not necessarily that all the codomain is used. domain is not necessary to be equals to range. If I have, I'm using numbers 1, 2, 3. I have 4, 5, 6. If 1 is produced to 6, 2 is produced to 5, and 3 is produced to 4. Such function is said to be an injective function. Similarly, if I have 1, 2, 3, then I have um 1, 2, 3, 4. If 2 is produced to 2, 1 is produced to 3, and 3 is produced to 4. This is still an injective function, which is same thing as one-to-one mapping. This can still be a mapping because mapping is it considered everything. Mapping can be number, it can be letters, it can be words. But for function, it must be numbers only. So that's how it works. So this is one-to-one mapping, and at the same time, it is an injective mapping. So what about subjective mapping? When is a function set to be subjective? Since you already know onto mapping, then to understand subjective mapping also will be very, very straightforward. Subjective mapping is the same as onto mapping. That is, for every input value, there must be one and only one output values, and all the codomain must be used. That is, codomain must be equal to range, and at the same time, the codomain must be at least an image of one input values of one element in the domain. Okay, I believe you got that. So let's say I have 2, 4, 6, 8. I have 5, 10, 15, 20. Okay, let me just use 5, 10, 15. So if 4 is produced to 10 and 4 is produced to 10, 2 and 4 are produced to 10, 6 is produced to 5, and 8 is produced to 15. You can see that all the codomain are used, and you can see that all the input values have at least one all the image rather all the image has at least is at least rather an image of one element in the domain. Okay, sorry, my bad. Sorry about that. Okay, so this range is equals to codomain. That's just for the subjective function. So the last one is the bijective function. The function is said to be bijective if bi means two, if it is injective, and if it is subjective. So how will you know? So therefore, let me get rid of this. This will be bijective if every element in the domain is at least an input value in the codomain. Let me just write this 1, 2, 3. Then I have 3, 4, 5, 6. So if 1 is produced to 4, 2 is produced to 3, okay, then 3 is produced to 5. Yes, this function is it is injective. It's injective, it is one-to-one, but it is not subjective. Not all the elements in the codomain are used, therefore it is not bijective too. So once one of them alters, is not bijective. So which one will not be bijective? When it is one-to-one, and at the same time all the codomain is equals to range, all the image is equals to the codomain. So I have 1, 2, 3, and I have 4, 5, 6. So if it is one-to-one, 1 is mapped to 5, 2 is mapped to 4, and 3 is mapped to 6, then it is bijective this way. You understand? So that's how to differentiate between the three. So let's consider a real world problem and see how they works. Okay. So this is a problem. Okay, that we need to work with. The question is state whether each of the following um, relations, A being mapped onto B, are function, injective, subjective, adjective, and we should also justify our answer. We should say the reason why they are or the reason why they are not. So let's focus on the first one, which is this. Is it a function or not? The first one. This is the first one. The relation between A and B. So you can see that the first dot is mapped to the first one. Second one is mapped to this. Okay. It turns out that this one is one to is like injective. Okay, it's injective. All the elements in the domain, okay, is mapped to different elements in the codomain. Though this one is not used, but that cannot alter the condition for injective. But at the same time, it's the function, because for every input values you can have one and only one output value. So it's a function and it is injective. That's we already have to answer. So it is a function because every input has one and only one output. Perfect. Okay. Now to have enough space, I'm going to get rid of that now. So it is a function. That's the reason. Okay, let me do it this way so that will be enough. It's a function. Oh, oops, sorry. Let me just get rid of it and put it proper. So it's a function. That one has passed. It is injective, yes, because um, different inputs has different outputs. It is injective. That's the reason. So you write it. Different inputs has different outputs. Is it subjective? For it to be subjective, all the codomain must be used. So it is not subjective. It is not subjective. And once it is not subjective, it means it won't be bijective. And it is not bijective. It is not because it is not subjective. Okay, so it is not subjective because range is not equals to codomain. That's it for the first one. For the second diagram, let's see. Um, for the second diagram, A is mapped to A. The first one is mapped to the first one. Good. This is mapped to this. This is mapped to this. This is mapped to this. So it is a function. Every input has one and only one output. It's a function. It's a function. Every input has one and only one output. That's the reason. Is it subjective? Different input has different outputs. That's nice. It is injective. It is injective. Different input has one and only one or different outputs. Okay. Is it subjective? You can see that all the codomain are used. So it is subjective because range is equals to codomain. All the codomain are used. Okay, all the elements in the codomain is an image of at least one element in the domain. So it is subjective. Once it is subjective and it is injective, definitely it is bijective. It is bijective because it is injective and subjective. And that's it, guys. So that's the answer to that one as well. So you will use the third one, that part C, for a practice problem. If you have any question, you can let me know. And if you want me to review your answer, you can just put it in the comment section below. I'm going to check it and give you a feedback. If you haven't subscribed to my channel, please do wait to subscribe to my channel. Thanks for watching. See you guys in the next video. Take care.